Okay, I'm Domenic DiFrancesco. I'm a researcher at the Alan Turing Institute in the UK, and specifically I work on what we call data-centric engineering. Today I'll be talking about the relationship between probabilistic models and decision analysis with the specific application of identifying data requirements. So I'm going to kick things off with a few quotes from some of my favorite stats books. Firstly, from Bayesian data analysis, they note that usually the reason we do statistics is to support decision-making. In James Berger's book, he says that there's these deep ties between decision analysis and Bayesian statistics in particular. This is a more engineering-y focus, and it makes the point even more strongly, suggesting that all problems of inference should also be considered as a decision analysis. And then finally, a quote from my former PhD supervisor from his book, suggesting that we should use statistics for organizing the process of acquiring knowledge to support decision-making. And it's that last application that I'll be focusing on today. So here is a decision event tree describing how some uncertain parameter could be related to a decision. We may perform inference on theta, and depending on our results, there may be different associated costs. And we can calculate the expected cost of each of these decisions. So here the expected cost of decision A1 would be this probability multiplied by this outcome, plus this probability multiplied by this outcome. And we can use that to then rank order our decisions, and we're usually looking for the one, or we're always looking for the one, with either the lowest expected cost or the highest expected utility. I'll use them interchangeably. This is maybe the simplest decision tree I could draw, and already it's becoming quite big. So typically what we do is we represent these as something called influence diagrams. And these are just Bayesian networks like the ones we saw this morning, with the addition of decision nodes and utility nodes. But aside from that, the principle is exactly the same. We're just looking to find our expected optimal decision, which is the one associated with our maximum utility. And there's lots of benefits to jointly representing our probabilistic models and decision analysis in this way. I don't think I've got time to go through my full list, but one of these benefits is it allows for some really powerful analysis to sit on top of that, such as calculating the expected value of collecting data. So here you can see I've changed this diagram to add a new decision node. We've got an option to collect some data of some type. And our expected value of this data is defined as the difference in utility with and without that data. The mechanism for where this value comes from is when we collect new data, we reduce our epistemic uncertainty about our system. And that may lead to the identification of a new optimal decision. Or even within the same strategy, we may just be exposing ourselves to less risk by better understanding our system. But essentially, the question that we're answering and quantifying is how and to what extent do we expect this data to facilitate improved decision-making. So hopefully to make things a bit more clearer, I'll talk through a few examples now. Yes, but firstly, just a quick note on software. It's been interesting to see the different software that we were working with. I've recently moved a lot of code into Julia, primarily because I've become quite fond of this decision programming library. This is just an extension to their optimization library, but it's built for working with influence diagrams. So let's look at one example problem first. Here, we've been asked to specify which ventilation setting we need to use for an office. We can run this on low, standard, well, or high ventilation. And increased ventilation rates will decrease the risk of infection from airborne diseases in this office, but they will cost more to run. So we've got a trade-off there where the outcome may or may not be intuitive. So we're going to formalize this process and represent it as a decision diagram. And you can see that our choice of ventilation setting will impact our uncertain infection rates. And the other thing that will influence this is how many people are in the building. There's a model for this that comes from Airborne, Cambridge, and there's a link to the paper in the slides, and I'll make the slides available. But we're calculating the probability of infection for an office with some known occupancy, known volume of the space, and an equivalent number of air changes per hour, which is our ventilation rate. But in this example, we don't know exactly how many people will be in the building. And so we need to average that over a probabilistic estimate. And here we've got a prior model, which is a Poisson distribution with a mean of 30. And we're going to find our best ventilation setting using this model first. And I'll just show you this nice syntax I alluded to earlier, where we build our influence diagram by adding our nodes, and then populate our probabilities and our costs, and then run the optimization. And if we do that based on that prior model of occupancy, we're told that we should select the standard ventilation setting, and this is our expected cost. But then what we can do is we can compare that to the case where if we measure occupancy. But I should also point out the important point that we don't know exactly what we will measure. So as you can see in this plot, if you follow this color bar, you can see that in instances where we detect very few people in the building, we're justified in using the lowest ventilation rate. As that increases, our expected cost increases too. Initially, because when there's more people in the building, there's a higher risk of infection. But then also because we eventually transition to a new optimal strategy, which is the next highest ventilation rate up. And that pattern continues. If we take the average of all of these simulations, which is shown by our dashed line here, and compare that to our cost before we hypothesized all of these measurements, this difference represents the expected value of measuring occupancy in the context of solving this ventilation problem. And that could be interpreted as how much should we be willing to pay for this data. So it's got a nice intuitive interpretation. Just a couple of notes on this result. You can see that this value is relatively low, just a few dollars. This is the value this data represents to us each day, so that would scale with time. And I've also labeled this the expected VOPI, where the P stands for perfect information, because I'm assuming that we can measure how many people are in the building without error, which is not the case in this second example I'll talk you through. So just to add a few different elements, we've got a different context here, but the idea is exactly the same. Now we have a problem where we need to identify a repair plan for different locations of corrosion damage, where we have repeated measurements at these different locations, and we can use those to trend the growth rate of the corrosion, the CGR, and forecast future degradation. So here D is the extent of the damage, T is the time of the measurement. It's just like a gradient in a linear regression. But we have the problem where the second inspection was incomplete. It was not able to visit this location, perhaps due to unsafe conditions or time constraints. There's lots of reasons why we'll have missing data within engineering. And what we're hoping to solve is the problem of, do we need to return to this location and take this measurement? Or are we okay to proceed with the information that we do have? So again, there's a link to a full paper with a more comprehensive description of the problem. But we can draw an influence diagram for this problem. And here's where I wanted to note the importance of prior models in this context. We've had some great talks this morning about eliciting prior knowledge. I think we've all had experience with needing to defend priors in our work. But I'd argue that they're especially important in this kind of calculation, because not only are they being used for updating and regularization and all the usual benefits of priors, but they're also being used to describe what we expect to measure. And so the reason I included this example in this presentation is because I treated this prior as a missing data point. And I've been using Bayesian methods for imputing missing data since I saw a talk at this conference, actually. by Richard McElrath, the author of Statistical Rethinking. He had this model of predicting the effect of cats being present on birds singing. And he talked about the case where he wasn't sure if a cat was in the room, and that was his missing data. And here I'm imagining this missing inspection location is our missing data. So here's some stand code where we're going to jointly estimate the corrosion growth rate and the extent of the damage at the location where we didn't visit and collect data. And this worked very well. So here's just 4 of these locations at the 2 different points in time. They're the 2 columns. And this unshaded density is the location where we didn't have a measurement and we've instead imputed that extent. And you can see we're getting a reasonable estimate. And we also have the desirable feature where we know this less precisely than if we had measured it. So that's a nice sense check for this to pass. So we can solve this using our prior model, add up all our costs for our expected repair plan, and compare this to the case where we do return to that site and take a measurement. And this is a histogram of all of those simulations, those samples from that prior, imagining if we were to measure all of those damage extents. And the results are presented in a similar way here, where this difference represents the expected value of this data to us. And here we can see that we should be willing to pay up to $2,500 to go and collect that data. And that's then an actionable result because we can compare that directly to a quote from an inspection contractor and decide whether we go ahead with the inspection or just progress with the repair plan using what we know already. Okay. So just a final few thoughts then. There's lots of benefits of considering our probabilistic models and the underlying decision problems that are, the reason we're doing the modeling. For considering them jointly is essentially it's because they work really well together. Points on some challenges of this kind of analysis. Firstly, I think it can be difficult in some cases to draw these influence diagrams at the time when a decision is required. And I'm thinking here of identifying future unforeseen sources of value in the data that maybe we can't think of at the time. But my response to this would be, we can only ever work with what we know at the time. And as long as we're careful and we document our analysis thoroughly, I think that's okay. And secondly, like with conventional experimental design calculations, there's often a problem of these being quite computationally demanding, which is an issue. But again, I'd respond to that by saying we can already do relatively sophisticated analyses of this type, and things are only getting better in that respect. In terms of further work, unfortunately, it's not ready at the moment, but I'm writing up a calculation that considered the opportunity to collect different types of data in different combinations and at different points in time. I've got some really interesting results there, I think, which I'll be happy to share with anyone who's interested once it's available. But for now, that's all I had for today. Thank you very much for your attention.